Good morning, students. I hope everything is well with you. Today we will start our lectures towards satisfying a new module which address the Boolean algebra as well as the logic gates. So let's get started. The reading material for this module will be your last section from chapter 1 of your textbook, as well as the first 5 sections of chapter 2. Before I proceed with the material for this module, I just got an email from one of your colleagues asking me to re-explain BCD. So guys, BCD in a nutshell is a way to represent a decimal digit using a binary code. So in decimal, we have numbers from 0 to 9, where 0 can be represented by 4 bits and 9 can be represented by 4 bits. 0 will be equal to 4 zeros and 9 will be equal to 1001. When it comes to representing 10, so 10 is a decimal number that should be coded using BCD in a different way than the regular binary format. In other words, 10 in decimal should not be equal, if I would like to convert it to BCD, to 1010. No, I should take 1 and represent it by 4 digits, which are 3001, and 0 represented by 4 digits, which are 4 zeros. That's it. This is MBCD. As a matter of fact, let me clear this first. As a matter of fact, BCD will give you a tool or a representation to encode just numbers in binary format. However, if we would like to encode alphabetical and numerical characters into binary, we should use one of the two prominent approach. The first approach is called the ASCII, which stands for the American Standard Code for Information Interchange. And this coding technique, the ASCII coding technique, uses 7-bit to represent any letter or any number, whereas the extended binary coded decimal interchange code, which can be pronounced by epicedic code, uses 8-bit to encode any letter. In other words, let's take a look as an example from our real life. So have you imagined that your keyboard is just an encoder? That's a keyboard. So if I would like to tell the computer that I would like to input a letter M, which is the first letter of my name, M. So how can the computer interpret that using the ASCII representation? I will look at the table here. Where is M? This is M here, guys. So M using the ASCII will be like sent to the computer by 7 bits, okay? 7 bits, starting by this one, which is the most significant bit, okay? 0, 1, 0, and 1, 1, 0, 0, okay? And if the computer would like to display M on your screen using the ASCII format, well, the controller will translate 0, 1, 0, 1, 1, 0, 0 into M. The same principle can be applied into the epicedic notation. In general, the ASCII is the most widely used one, and it has been used with multiple I/O controller. The epicedic was used on some IBM machines, and it's now obsolete. Okay, now let's get back to our main topic, which is Boolean algebra and logic gates. So why do we use Boolean algebra? and logic gates? The answer is so simple. It's basically to describe how digital circuit works. Let's take a look on this simple example. So basically I have a light switch circuit here, and this light switch circuit contains a bulb as well as an outlet, and then we have a switch somewhere, okay, and that switch is connected back to the outlet, because we would like to have something that provide positive and negative so the circuit can work. So how does this circuit work? Can we describe it? The answer is basically yes. So if the switch is closed, if I have my switch here, and if that switch is closed, that means the light will be on. If that switch is open, that means the light is off. Okay, so this interpretation of an electrical circuit is called Boolean expression, because remember, Boolean deals with binary, and binary means 1 and 0, which can be translated to on and off. Okay, guys? Let me give you another example here. Okay? And suppose that this circuit simply is, I have one switch like this and another switch like this. Those switches are connected to each other. That is A and that is B. I have here like a bulb somewhere. Okay, and here I have my battery. Okay, so that's plus and minus. So how this bulb is working? How can we indicate that the light here is working or not? So if switch A and switch B are closed, then the light will be on. Otherwise, even if the switch A is closed and switch B is not closed, we will still have an open circuit and no light will be shown here. Okay, guys? So what are the, how can we express all the combination of switch A and switch B as well as the light? So we have here A, B, and the light here. Okay, so if A is, let's say it's open, and B is open, that means the light will be off. Okay, and if A is open and B is closed, the light is still off, because both of them have to be closed for the light to be on. If A is closed and B is open, the light is off. Okay, if A is closed and B is closed, the light will be on. Okay, so this representation, if we translate it to a binary, okay, so the open indicates 0 and the closed indicate 1, the off indicates 0 and the on indicate 1, that we will have something similar to A, B, and the light is, let's refer to the light by the output here, F. So we will have 0, 0, 0, 0, 0, 0, no, that is 1, because that's closed, and 0 and 1, 0, still 0, and 1, 1, that is the only case which will have 1. This representation of a digital circuit is called a truth table. Okay, guys? So, Boolean algebra is an effective way to describe how electronics are interconnected with each other and how we can optimize them. That's what we will see in the next slides. Okay? Now, even though it's outside the scope of this course, I will show you in details how these digital electronics works. So let's take a look on how the switch can be implemented using digital circuits. So we have something called a metal oxide semiconductors, MOS transistors. These transistors can be symbolized in Na. Okay, the transistor, guys, here basically has three terminals: terminal A, terminal B, and or 1 and 2, and the gate. The gate is like a security guard who's waiting. If we apply a positive voltage on the gate, this circuit will be closed. If we apply the negative voltage on the gate, the circuit will be open, so the switch will not be like conducting or working. So if we apply 2.9 or above, this circuit will be closed, and basically we will have a short circuit between 1 and 2. Okay, guys? Now, the question is, how can I use two MOS transistors to implement a NOT circuit? If you remember the complement, guys, we want, like, we have 0 and we want to get like 1, and if we have 1 we need to get 0, or if we have high I want to get low, and if I have low I want to get high. So how can I implement that using the digital electronics principles? Now, the way that I can implement it is using two different types of transistors. The first type of transistors is the N type, which we showed early in the previous slides, and the second one is the P type. Okay, the P-type transistor will work in the opposite way of the N-type. In other words, if you apply a positive voltage, electrons will flow when a voltage of 0 is applied to the gate. So the circuit will be closing like this. So 1 will be equal to 2. And if we apply a voltage of 2.9 and above, the gates will be open, no electrons will flow, so we'll have open circuits. In other words, this line will not be conducting, or will not be shorted. So in order to implement an inverter, what can we do? We can use both the N and the P-MOS transistors connected in serial. Okay, let me show you what do I mean by that. Okay, guys? So basically, we have here that is this is an electronical circuit, and this electronical circuit, you can go and buy the transistors and you can attach them this way. This is outside the scope of this course, but I just want to show you for the sake of education. Okay, so basically, guys, so we have this circuit, we have the input and we have the output. Let's take a look. If we apply like a 0 voltage, so what will happen? And if we apply the 2.9 voltage, what will happen? If we apply a 0 voltage, the P-type transistor will get conducted. You remember, because the gate will close and this line will be what? Will be conducting. So what does that mean? That means I will get here, and this one, on the other hand, the N-type will not be conducting. So I will get here 2.9, because this point will be equal to this point, 2.9 volts. Okay, let's take a look on the, yeah, let's take a look on the other possibility, like if the N voltage is equal to 2.9, which represent the high in our case. If we apply 2.9, the P gate, the gates of the P transistor will be not conducting, will not close, no electrons will pass through. As such, this will be open. However, the N-type will work, will be closed. You see that? But since here we have, since here, guys, we have here like the voltage will be taken from this point, because this point will be equal to this point, because this is like the same circuit or the same wire, and we will get a 0 volt at the output here. Okay, so as we can see, guys, we can describe the operation of digital electronics using Boolean expression. So in other words, if I have 0 volt at the input, I can get the output will be 2.9 to describe this circuit. If I have 0 volt at the input, I will get 2.9 volts at the output. And if I get 2.9 at the input, I will get 0 volt at the output. So this thing can be rewritten again as, if I have this N to represent X, and this will represent Y, and Y can be represented by X inverted here, because I'm just inverting that X. Okay, so if X is equal to 0, Y will be X prime, and its inverted will be equal to 1. Okay, and if X is equal to 1, Y will be equal to 0. Okay, this is the truth table, guys, of this digital electronic circuit. Okay, so guys, in general, all digital electronic circuits can be described using 3 operations and 3 different types of logic gates. Those operations are basically the inverter, which we just covered, and the inverter can be symbolized using a triangle with the circle at the beginning. So we have X as the input, and we will get X prime at the output. And this is the truth table of this inverter circuit, as well as I showed you that we can we can implement or we can describe a circuit using the AND operation. And please take a look that the AND has 2 inputs. Okay, and the symbol of the AND is represented by this. So the AND is called all or not. Okay, so the inputs has or everything or not. So in general, the AND is called everything or not. Okay, why the AND is called like all or nothing gates? Because the AND will only get you like an output of 1, which represent high, if both inputs are equal to 1, or if both inputs are high. Okay, guys. Okay, now the way of writing like Y equal to X prime and C equal to A, B, okay, this is called, you know, a Boolean expression or a Boolean function. We will cover it later on today, but I just want to emphasize the fact that the symbol to represent the AND is using the dot here, and please do not be confused by the binary multiplication. Okay, the other type of representing any digital circuit will be like the OR condition. Okay, and the OR conditions, if we like do it again, like, you know, using our bulb example. So if I have here a switch, and if I have here another switch, okay, and this is A, and this is B, and both of them are now connected to, okay, and both of them are connected to some bulb here, okay, and then I have here a battery, okay, of 5 volts, and then I connect that. So if A is closed, I will have a current, so the light will be on. If B is closed, I will have a current, and even though if A is open, I will still have the current. The current can go this way, and this way, and this way, and then I will still have the light. So in other words, the OR is a condition that can be described by or it's a gate that can be described by any or all gates. So if any of A or B is conducting or is closed, I will have an output. If I apply that, guys, using the truth table representation, the output will be 1 if any of A or B is 1, or if both of them. Okay, the simplified representation of an OR gate is by this simple, and the Boolean expression of any OR gates can be written by using the plus. And please do not be confused by the arithmetic addition. So guys, if I apply the principle of these basic logic gates, I can form a more complicated function. Let's take a look on this function f. This function f is the output of a combinational logic circuit that is equal to x and with y prime, z and with x prime. Both of them are OR. So f is the function of this f is the name of this function. The term, yes, so the terms, if I have any letters and with any other letters, okay, or yeah, anything separated by, okay, let me wait. So I can apply what I have learned here to form a more complicated function. Let's take a look on the function here f. So f is the name of this Boolean expression, and this Boolean expression is being implemented using the basic logical operations, which are the AND, OR, and the inverted. So anything separated here by the plus is called a term. Okay, so the term is an implementation with the gate. In this example, we have two terms, x, y prime, and z and x prime. Okay, z and x prime. So x, y, and z are the input variable, each representing 1 or 0, or low and high. Okay, a literal here is the occurrence of an input variable or its complement. So this function here has how many literal? So this is a literal, okay, and this is a literal, and this is a literal. So we have time is a literal. So we have literally 4 literals, which are x, y, z, and x prime. Okay? Now, we should pay attention to the precedence that Boolean operations occur. So if I have this function here, f equal to a, b plus c, how can I read this function? Is it ab ORed with c, or is it a ANDed with bc, b plus c? So the answer is definitely it's AB ORed with C, because the priority of any Boolean algebraic operation is as the following. First, we have to satisfy the brackets if or the parentheses if we have, then the not, the inverted, or the complement. Then after that, the and will come, and at the end is the or. Okay, that's why I told you the term is anything separated between the or. Okay, guys. So if I have a plus b dot c, here I should apply the priority here, and the first thing to draw is the OR gates between input A and input B. Okay, so it's the OR gate. Then after that, both of them are AND with C. Okay, so the parentheses are needed to represent this like Boolean function. Okay, so basically we learned how to describe any digital circuit using a Boolean expression, which is basically the Boolean function, as well as using a truth table. Another way of representing a Boolean expression is using the waveform. That is what you're gonna do, guys, in the labs. So the waveform is basically, like a square or a train, waves here, at which, when you go up here, that represent a high or one, and if you're down, that means, that means you having like a zero logic, okay, or a 0 volt here. Okay, so so we have here like two inputs. So x is represented by 0 here, and here we still at the high voltage, so it will be 1, and here we still at the high voltage, it will be 1, and here, okay, the it's 0, and here it's 0. Please pay attention to the to the length of that waveform. So we have, this is the length of our waveform, and that's why we took 0 here, and at the same length here we took 1, and at the same length here we looked at the signal and it's still 1. That's why we took 1 and 0 and 0. And then y here, it's represented by 0 0 1 1 0. Okay, so if I wanna and x, or if I would like to find x ANDed with y, so 0 ANDed with 0, the answer is 0. 1 ANDed with 0, the answer is 0. 1, when it's ANDed with 1, apparently I'm gonna get 1. 0 ANDed with 1, apparently I will get 0, and so on. If I would like to get the OR, so 0 ORed with 0, it's 0. If any of them are 1, I'm gonna get 1 here. If here both of them are 1, so I'm gonna get 1. Here it's y is 1 and x is 0, so I'm gonna get 1. And when both of them are zeros again, I'm gonna get 0. Okay, if I would like to, and please take a look at this, so this is x, and xy was like this. Okay, so if x inverted will be like high, then it's the opposite. Okay, so this will, if that was 0, this will be 1, this is 1, this will be 0, this is 1 will be 0, and this is 0 will be 1. Okay, guys? Another important information, guys, that both and OR gates may include more than two inputs. So let's take a look here. We can see here a symbol of an AND gate with three inputs, namely A, B, C, and the function f will be equal to A and B and C. And on the right side here, we have a symbol of an OR gate with four inputs, namely A, B, C, D. And the function here, G, can be described as A plus B plus C plus D, or A or B or C or D. Now, the important question here is how to write the truth table of the function f. Okay, so basically, guys, a truth table will contains all the possibility of the inputs with the corresponding output. So how many inputs we have, guys? We have three inputs. What are the possibility of each input? Is two values, either 0 or 1. So it's basically 2 to the power 3, which is equal to 8. That means my truth table has to include 8 possibility with their output. So let's take a look here. So I have A, I have B, and I have C, and I have the output, which is F here. Okay, so here 0, 1, 0, 1, 0, 1, and 0 and 1. Okay, and here I have 0 and 0, 1 and 1, 0 and 0 and 1 and 1, and here I will have 0, 0, 4 zeros and 4 ones, 1, 1, 1, 1. As you can see, like this representation will include all possible combinations from 0 decimal up to 7, which is equal to 8. Okay, so if I add A and B and C, the output F should be equal to 0. Will be equal to 0. All of them will be equal to 0 until I reach the final case. But because you remember, it's, this AND gates will be will produce 1 only, like if and only if all the inputs are in the high states or are equal to 1. So that's equal to 1. So as an exercise, guys, I would like you to write the truth table of function G here. Okay? Okay. As a matter of fact, guys, any Boolean expression can be implemented with the three basic logic gates, which are the AND, the OR, and the NOT. Let's take a look on this example. So we have function X. This function basically has 5 inputs. Okay, but how we gonna implement them with logic circuit? So basically, let's remember the precedence of logical operation. First of all, we have to satisfy the parenthesis here. Okay, so I have first to OR C and D. Okay, and after that I should AND it with A, and then I have to invert the output here. Okay, then after that I should OR it with a B and E. Okay, so this is how we implement our Boolean expression function X. Okay, so that is for today, guys, and I will see you in the next one. Thank you so much for watching.